The Habitat for the Exploration of the Lunar Polar Surface, or HELPS habitat, is a durable, low-mass lunar habitat designed by the Senior Aerospace Engineering Design Team at the University of Maryland. This team is comprised of 21 undergraduate students, our graduate advisor, Zach LaChance, and our 4 faculty advisors, Dr. David Aiken, Dr. Mary Bowden, Dr. Andrew Becknell, and Dr. Jared Young. Our team's mission statement is to advance the future of space exploration by establishing a sustainable settlement for humans on the lunar surface that enables the execution of EVAs and meaningful scientific research. Our habitat is a reusable habitat which will be ready for launch by 2028. This habitat can house a crew of 2 for 30 days and has extensibility to both future Moon and Mars missions. The habitat's dry mass is 6,000 kilograms with a 30% mass margin built into those calculations, a diameter of 3 meters, and a length of 6.3 meters. Here we have an internal cutaway of our habitat. Starting from the right side of the habitat and going to the left side of the screen, we have our driving station where the astronaut can sit down comfortably and look out both the windows and at our monitors in order to steer the habitat. Then we have our flexible exercise and work area, our environmental control and life support systems, as well as storage and bathroom area, and finally our suit ports and suit lock system. As you can see, our habitat is primarily powered through 2 solar cells. These solar cells can pivot on an axis to track the sun in order to maintain optimal energy generation. Now, the most innovative feature of our habitat is that it is a mobile habitat. It is a 6-wheel mobility system which allows this habitat to traverse the lunar terrain in order to expand the field of operations of our astronauts.
Getting to the moon isn't easy, but there are many existing systems that we can use to get there, such as launch vehicles. We wanted a launch vehicle with capacity to get our payload into lunar transfer orbit. We needed a payload capacity to support our habitat mass, enough payload volume that we only needed 1 launch, an affordable system, and a system with a high technology readiness level. Therefore, we chose the Falcon Heavy as our launch vehicle. There are many other steps we still need to take to get to the moon. We needed to perform a maneuver to get into NRHO, at which we would rendezvous with Gateway. Then our CARES module would detach and perform a phasing maneuver. Then our habitat can be loaded into an HLS, which would take us to the lunar surface, where our habitat would be unloaded, and then our habitat can perform its mission on the lunar South Pole. In order to get into NRHO, there are 2 maneuvers that we need to perform. One is during a flyby of the moon, which would require 178 meters per second, delta V, and the second is a 250.5 meter per second delta V insertion burn into NRHO. These total to under 450 meters per second. In order to perform the phasing maneuver that our relay satellite needs to do, in order to be 180 degrees out of phase with Gateway, a delta V of 200 meters per second is required, as well as 10 meters per second per year for orbit maintenance. In order to land on the moon, we had a choice of 3 different landers. The National Team Lander, which has the capacity to deliver large payloads with a 7.2 payload capacity and has a crane to unload payloads from the top of it. The Dynetics Lander, which was focused on astronaut transport but has the capacity to switch out the crew module with payloads such as large rovers or habitats, and the payload is very close to the ground, allowing for very easy unloading. And the SpaceX lander, which has a 100-ton payload capacity and uses a crane for unloading. Based on the criteria that all 3 of these systems have, our habitat would be compatible with any of the 3, regardless of which NASA chose to work with Gateway to land astronauts on the lunar surface.
With our mobility feature in mind, we set out to pick a landing site for the habitat. Our primary considerations were solar illumination, line of sight to Earth, low slopes, and access to regions of scientific interest. We looked at various topographical maps and used NASA's Moontrek application to select the site shown in the image that is about 15 kilometers from Shackleton Crater. It has high illumination, a relatively long period of line of sight to Earth, and low slopes nearby. We then constructed a path for the habitat to traverse during the first 30-day crew mission. Shown in red in the image, the path is a 36-kilometer loop that circles a small permanently shaded region and also allows for access to Shackleton. The numbered circles indicate places where the habitat would stop for crew to conduct EVAs. The path adheres to the constraints of traveling no more than 3 kilometers per day, staying on slopes under 10 degrees, and staying within 15 kilometers of the lander. The black loop includes points 3 kilometers from the path, so crew would be able to explore any region within it. We then developed a 30-day timeline to go along with the path. It is broken down into 4 weeks of activities with arrival and departure days that bookend them. There are 15 days that would consist of EVAs and 11 for purely internal operations that includes 1 rest day per week. The other 4 are reserved as backup days where the crew can decide what to do based on how the mission is going. These can occur on any day, not just the ones indicated, and would simply shift the timeline around. When illumination is poor at the South Pole, crewed missions cannot be conducted, so after the first set of missions at the landing site, the habitat will be uncrewed. During this extended period of time, the habitat will be driven remotely to a new landing site and be there in time for the next sets of crew to arrive the following year. The image shown provides an example path between our first landing site and one of the others we considered.
Habitat mobility will lead to several benefits throughout the duration of the 30-day mission. When the lander arrives on the lunar surface, the component of mobility will make it easier to unload the habitat. Once the astronauts are safely inside the habitat, mobility will allow them to access scientific areas of research within 15 kilometers of the lander, increasing the possible exploration area by 36 times. While astronauts are performing EVAs, the habitat can autonomously drive beside them, making it easier and safer to get research done on the moon. After the initial mission is over, the habitat can relocate to other areas of the moon to conduct new missions. For future lunar missions, the habitat could relocate to new mission sites and serve new crews of astronauts without needing to deploy an additional habitat. It could also allow for larger crews of astronauts by docking with an additional mobile habitat. A crew of 4 could be comfortably accommodated using 2 helps habitats that are driving together using a wagon-like configuration. The mobility system results in a mass increase of roughly 500 kilograms, as well as a 1.4 kilowatt increase in power required. Although the habitat only moves once every 2 to 3 days, the mobility system accounts for 30% of the power drawn. Our team firmly believes that these benefits of habitat mobility outweigh these drawbacks in mass and power.
So there are several components on our habitat that need to be stowed in order to actually fit into our Falcon Heavy launch vehicle. And the one-time deployment of all these things will be done with hinge joints and springs held in place by pyrotechnic bolts so that they can be deployed at the proper time. The wheels will be deployed before lander integration so that we make sure that we can actually get off of the lander once we're on the lunar surface, and the rest of the components will be deployed afterwards. Here's an animation of the deployment sequence. We start off in our launch fairing, and the propulsion module, which is at the top right now, is what takes us over to Gateway. Once we're docked at Gateway, the propulsion module attaches. We start integration with the lander, and the wheels are deployed. And once we're at the surface and land safely far away from lander, all of our solar panels, cameras, and platforms deploy. So for design the mobility system, we had a few requirements, including being able to traverse 10-degree slopes, capable of steering, having a great suspension, and be able to overcome the obstacles that are typical of PSR regions. We also had to comply with the minimum bearing capacity, which so that we can actually drive around without sinking to the ground. For the wheel design itself, we did terramechanics studies, looking at various wheel diameters, various wheel widths, and number of wheels. We also looked at grouser sizing and number so that we could get extra tractive effort, all in order to produce positive drawbar pull on our maximum 10-degree slope requirements, which a graph of which you can see on the top right. So in the end, we decided on a 6-wheel drive, which was had added redundancy over a 4-wheel drive system and was capable of a wider range of slip values. And with our 0.6 meter diameter, 0.3 meter wide wheels, we were able to get a 5-wheel contingency so that if one of our wheels fails or one of our motors fails, we can actually continue driving with just a small amount of reduced max slope capability, depending on the slip ratio of the lunar soil, which is actually an unknown. For drive system design, we went with a DC brushless motor, which is more efficient, had lower maintenance than alternatives. And to produce our 1,000 Newton meters of torque required for flat terrain, we have a high gear ratio harmonic. We don't mind the high speed reduction because we're only traveling at 0.5 meters per second. And to drive at this speed, we're consuming about 3.5 kilowatts, assuming 85% efficiency. For the steering design, we went with overwheel steering, which we thought was favorable over alternatives like skid steering because of its very low steering torque. So with a 0.4 meter squared contact patch, we end up needing about 130 Newton meters of steering torque. And this is again accomplished with a high gear ratio harmonic because since we're not driving very fast, we don't need the steering to be very fast either. We also conducted some stability analysis to make sure that our habitat wouldn't tip over at the various slopes that we're looking at. So on the left side is our nominal limit of 10 degrees. The red line is showing the furthest point where CG could be placed such that the weight vector crosses the wheel contact patch, and that's our stability limit. So you can see that the CG can be pretty far displaced forwards or backwards on the side view of the habitat, and we are still stable. And the same is true for 20-degree slopes, which we decided to design for in order to super assure ourselves that the habitat wouldn't tip in any situations, because having the habitat tip and potentially having a rock puncture the pressure vessel would be catastrophic. And the same is true here for cross slopes, that we could, our habitat is still quite stable on cross slopes, and it won't tip left or right.
To help dampen the forces that the habitat will be experiencing when moving, a double wishbone suspension design was added. There are also 2 habitat legs that will be attached to the outer supports. These are for stability as well as leveling the habitat. There are three windows on the driving end of the habitat. One main window for viewing the path directly ahead, and 2 smaller side windows for viewing the potential terrain obstacles. For material considerations, we'll be using an aluminum 7075 T6 for the pressure vessel, due to its high yield strength as well as its low density. For the pressure vessel design, we will be considering a cylinder with ellipsoidal end caps, a cylindrical section length of 5.5 meters, a radius of 1.5 meters, an ellipsoidal end cap radius to height ratio of 2:1. There's also an isogirt structure that is around the habitat. This will allow for a thinner material while also having the strength of a thicker material to prevent against buckling. The chassis is a rib-like structure that will allow for all 6 wheels to attach to the habitat. There are 2 outer ring supports that attach to the end caps. These will allow for attachments of things such as solar panels, as well as some cameras and other systems. In terms of shielding, we'll be using a Whipple shield to protect against micrometeoroids and orbital debris. This will be a 1 millimeter thick aluminum 6061 shield at 15 centimeters offset.
We began by breaking our habitat into 3 primary volumes: the suit lock, logistics segment, and habitation segment. We'll first examine the habitation segment, where the crew carries out most of their tasks while inside the habitat. We can peel away the outermost layer of the pressure vessel to reveal roof-mounted stowage racks that serve as passive radiation shielding. Next to each berth is an additional water tank shield. On the front of the habitat, there are 4 additional stowage volumes and primary and secondary driving windows. We can remove these stowage racks to reveal the inside layout. On the left, the red astronaut occupies a stowable work surface with a privacy curtain separating it from the other half of the habitat. The green astronaut sits at the front driver station, supplemented by displays and physical windows to aid in driving. And on the right, a berth is fully deployed with its privacy curtain separating it from the habitat. We focus on flexibility in our design, and we show that here in 3 primary configurations. On the left, work surfaces are fully deployed with a privacy curtain separating them, allowing for private work to be done. In the middle, this privacy curtain is stowed, leaving a singular large work surface for group work tasks. And on the right, we stow half that work surface for more open volume for group recreation activities. Sleep is done in the same volume with 2 fully deployable berths, with privacy curtains separating it both visually and orally from the rest of the habitat. Exercise is also done within this portion of the habitat. Resistance training is done using a dual cable device integrated into the floors with cables independently routable to either half of the habitat. By making the cables routable, we increase training variety, and we enable simultaneous single cable exercise. Aerobic training is similarly done in this area with a cycle ergometer chosen based on Cevas flight heritage, making a low mass, low volume system that can be stowed between use.
Our driving station will consist of a large center window with 2 smaller windows positioned below and to either side of the main driving window. 2 monitors will be placed on either side of the main window that can be used to display data from our side-mounted obstacle avoidance cameras. Additional storage for CTBs is located in the overhead space above the driver. The rendering on the right shows the approximate sightlines from each of the 3 windows. 2 smaller windows are positioned to provide a clear view of the front of the 2 wheels. The docking port on the port side of the habitat will be used as a secondary mode of resupply between different habitats, while the suit lock will be used as the primary method to bring cargo into the habitat. Once all of the CTBs have been loaded into the suit lock, it can be pressurized and the cargo can be unloaded into the habitat through the access hatch. Below is an estimate for the amount of cargo that each crew will bring with them at the start of their mission. The EVA suits will be mounted side by side on the internal bulkhead. with the starboard suit port being mounted inside of a 2-meter tall standing access hatch. This hatch port design will allow for easy access to the suit lock without sacrificing wall space, and without requiring the astronauts to access the suit lock via a crawl-through access hatch, minimizing the transfer of dust to the crew's clothing. Our habitat will also include the addition of a retractable standing platform that will be located at the outside of the suit lock and will provide sufficient enough room for an astronaut to turn around comfortably while in their suit. The suits that we will use are NASA's XEMU suits and feature improved mobility and rear hatch entry for use with our suit ports. Each suit is custom fit to the astronaut and can be connected to either of the standard size suit ports. Now we'll begin our section on life support and crew health. To start off, I'll talk about crew health requirements. According to NASA documents dictating the standards for crew health, we can categorize our mission into Level 4 requirements. This is defined as a planetary mission lasting more than 30 days where immediate return to Earth is infeasible. To satisfy this requirement, the crew will be required to carry a basic first aid kit as well as a portable defibrillator.
The logistics segment has an off-center hallway, allowing for a shallower stowage volume on the left and a deeper volume on the right. In this deeper volume, there's a stowage rack, the restroom, and the docking adapter. We introduce flexible stowage racks that can accommodate both standard CTBs and other payloads. In these racks, life support is also housed and positioned far from the crew quarters to limit noise pollution. We also accommodate underfloor stowage, allowing us to store additional triple CTBs.
For our habitat, we've selected an 8.2 psi, 34% oxygen, 66% nitrogen atmosphere. This atmosphere meets all human physiological requirements and allows for rapid pre-breathes in order to facilitate EVAs onto the lunar surface. Oxygen and nitrogen will be provided by storage tanks in an open-loop system, and the atmosphere will be maintained by a 4-bed molecular sieve, as well as air filters and moisture control systems. Here you can see some of the other life support systems in the habitat. This includes a VAP car for water processing, as well as a universal waste management system and a heat melt compactor for waste management, as well as a fine water mist fire extinguisher for fire protection. The location of the 2 fire extinguishers can be seen here. If we were to locate one fire extinguisher centrally in the habitat, it would only be around 2.5 meters away from a crew member at any given time. However, for redundancy and to ensure that crew members always have access to a fire extinguisher in the habitat, we've included 2 fire extinguishers at the 2 most used parts of the habitat, being the crew quarters and right next to the suit lock. Here we have a snapshot of our radiation trade study. We decided to use water walls as they utilize mass that's already available to us in our mission and does not require additional mass such as a polyethylene shield. Additionally, we plan to use boulders as they are available. However, we are not dependent on boulders. If we happen to be close enough to a large enough boulder to provide protection, we can certainly use the mobility system to position ourselves behind the boulder in order to get that little bit of extra protection in the event of a solar storm. Here, you can see the orientation of our habitat during one of those storms. The boulder may or may not be there, otherwise the orientation would be the same. Crew members will be protected longitudinally by the rest of the habitat, including all the life support systems, and they will be protected radially by the water walls as well as the overhead CTB stowage. It is worth noting that because of the 30-day short duration of our mission, we are not overly concerned about GCRs and are mainly concerned about solar particle events.
In order to enable continuous communication between the habitat and Earth, an intermediate communication system is necessary when direct line of sight from the habitat to Earth is not possible. The optimal relay satellite configuration would include the use of ComSat alongside Lunar Gateway in its near rectilinear halo orbit. After delivering helps to Gateway, the propulsion module will detach and establish 180 degrees phasing with Gateway for subsequent operation as ComSat. This would save a lot of money, upwards of $100 million, as it would not require an external launch, and again would reuse the propulsion module itself that would be delivering helps to Gateway to take on the requirements for the relay satellite. In terms of these requirements itself, there are 2 main responsibilities for ComSat, first being the communication relay as previously mentioned and enabled by the parabolic antennae and 2-way transceivers, and the second responsibility being navigation, which ComSat will serve as an eye-in-the-sky navigational aid for the actual habitat itself. ComSat will be equipped with central avionics box, a laser altimeter, cameras, communications equipment, and solar arrays. The electronic box at the heart of ComSat will have a central computer, ports, wiring, and power supply. and these components will be radiation hardened. The laser altimeter system itself will be analogous to the lunar orbiter laser altimeter aboard the LRO, which will measure range and lunar surface features to aid in the surface navigation. The telephoto and wide-angle camera lenses will be used to take pictures of the habitat on the lunar surface for position determination. These cameras will be capable of discerning surface features to a resolution of a couple tens of meters from NRHO, and the 1.5 meter parabolic high gain antennae will be pointed at both the habitat and the Earth and be used alongside JPL's IRIS V2.1 deep space transponder for communications. IRIS will upscale and downscale between S and X band radio frequencies to be able to enable these communications. In terms of communications themselves, it's important to note that link margins will need to be at least 3 decibels or greater for accounting for inefficiencies and errors in transmissions at both ends. You can see on this first link here between directly helps itself on the lunar surface and Earth, we have link margins of 3.89 decibels and 4.45 decibels for S and X band frequencies respectively. In terms of the other link going between helps and using the communication relay satellite itself, for S and X band, again, we have link margins of just above 3 decibels, and we'll use the parabolic high gain antennae. And then in terms of going from the actual communication satellite to Earth, using S-band, again, you can see there's comfortable link margin. And it's important to note that for each aforementioned link, will support up to 50 megabits per second data rate, with the exception being the omnidirectional antennae that will be direct to Earth, which we use primarily as a backup and will support 20 megabits per second of data transmission. It'll be important to accommodate 4K video at 30 frames, and newer compression codecs will estimate about 6 megabits per second as the highest data rate for a single video feed, and this will be a major constraint for our communications. So that would mean we would need to have data storage. An example solid state recorder from Airbus in flash memory with 12 terabytes of capacity will enable about a week's worth of simultaneous video feeds running at this 4K resolution.
So the harsh conditions on the lunar South Pole drove design requirements for both our power and thermal system design. So that's a low solar elevation angle from 0 to 3 degrees and long periods without illumination. Our power system needed to be able to provide 4.5 kilowatts of electric power. This is supplied by solar panels and a radioisotope thermoelectric generator, or an RTG. The solar panels are designed to fully power the habitat, with the mobility system being powered by stored energy in the batteries. We had 12 meters squared of solar panels to generate our necessary 4.5 kilowatts. This is using cells from Spectralab with a 27.9% end-of-life efficiency. And these are able to collect the 22.5 kilowatt hours we need for the mobility system over the course of 24 hours. Energy is stored in lithium-ion battery packs for a total of 30 kilowatt hours. This is 3 separate packs for redundancy should one of them fail. They have 125 watt hour per kilogram energy density with 98% efficiency in charge and discharge. And each is contained in a separate box, which provides thermal control, so heat dissipation as well as heat generation, depending on if the batteries are running hot or cold. For the thermal control system, the temperature requirements were the driving constraint. We're using separate loops for interior and exterior components, with multi-layer insulation covering the exterior to reduce heat loss. Our 2 loads of concern were the hot case, which is when we're in full illumination and all systems are running. This is around 8.25 kilowatts of required heat dissipation. And the cold case, where we need 50 watts of input heat to keep the habitat warm. Internally generated heat is radiated through a portion of the upper habitat structure, with heat generated by the motors being rejected through fenders mounted on the wheels. The solar panel waste heat takes advantage of the large area and dissipates heat through the back of the panels. This came out to a radiator area of 13.5 square meters for the pressurized volume, 2.5 square meters for the motors, and 12 square meters, which is the same for the solar panels. To confirm these results, we ran a finite element thermal analysis. And as you can see in the plot on the right, the habitat is mostly isothermal at our desired temperature of around 295 K, which is around room temperature. Low light conditions were a main driving factor in our design considerations. We need the habitat to be able to last for multiple mission cycles, multiple crews coming through. So to provide electricity when the sun goes down, we decided to include an RTG, which provides 110 watts of electric power. This will provide the 50 watts of input heat we need to generate in the absence of sunlight to keep the habitat warm, and any excess energy will be used to power communications and other systems intermittently when we need them. Our final design point was the propulsion module. This was needed to provide delta V for our dock with gateway and to double as a communication satellite. We had a total delta V budget of 770 meters per second. This was 450 meters per second for the dock with gateway, 200 meters per second for phasing maneuver for the communication satellite, and 120 meters per second for attitude control and station keeping. We decided to use hypergolic propellants rather than cryogenic propellants due to superior storability. And the large available payload mass in the Falcon Heavy mitigated any concerns in ISP for the hypergolic propellants. We decided on MMH and N2O4 as our fuel and oxidizer at a mixture ratio of 1.7. This was to keep the tank sizes approximately the same. We're using a pressurized helium feed system rather than a pump feed system due to the simplicity and the lower power requirements. And pressurized gas feed system was sufficient for our requirements. We also included a external solar panel to provide 300 watts of electric power the communications and the valves for the propulsion system. This came out to around 1,768 kilograms of total mass with a 610 kilogram inert mass.
Our habitat has a dry mass of 4,150 kilograms. This mass gives us a 50 kilogram growth potential while still maintaining our 30% mass margin. In the graph to the left, you can see our mass breakdown by the different subteams that we have. This image depicts our work breakdown structure. It shows the different sections that we split the project into, and then the sub-levels of each of those sections. These sub-levels were then associated to one of the subteams that we created. This helped us with our cost estimation. For our cost spread, we had a beta function, but with that beta function, we exceeded our budget cap from 2023 to 2027 by $2/3 billion, so we distributed that money between 2022 and 2028. You can see the breakdown of that money in the table to the right. For scheduling, we decided that we would break it down by the different phases that the project would go through. And so we start with the concept and design reviews to ensure that we're picking the best design, then go into requirements, and then ultimately go through procurement, testing, assembly, and integration.
The lunar habitat design could be implemented on Mars with a few modifications to the mobility and power systems. The higher Martian gravity would increase the max torque requirements of the mobility system to 3,150 Newton meters, which requires an additional 1.3 kilowatts of power and 300 kilograms of mass to implement on Mars. The power requirements and power generation capabilities would also change in a Martian environment. Mars has a day-night illumination cycles of 12 hours each, and the solar flux is 2.3 times greater on the moon. Therefore, solar panel area would need to increase by a factor of 7 to provide the habitat with the same mobility capabilities as in the lunar mission. In the case of severe dust storms, illumination could be blocked for extended periods of time. For crew safety, it may be important to include invariant sources of power like nuclear power generators or regenerative fuel cells to supplement solar power. The benefits of habitat mobility are lessened in a Martian environment. Because of the nature of Martian day-night cycles, illumination does not vary by location as greatly as on the moon. Meanwhile, the impact of mobility on the dry mass budget would increase from 9% on the moon to 16% on Mars. However, mobility would allow astronauts to explore larger portions of the Martian terrain for scientific research, allow the habitat to distance itself from the lander during takeoff and landing, and allow for autonomous repositioning during uncrewed portions of the mission.